Hi everyone, this is Dr. Venkateswarlu, working as a professor of EEC at IARE. Yeah, today we will discussing about LMSE, least mean square error filter design. Yeah, so this is all coming from that digital filters, and basically we are having the two filters. One is IARE and FIR, infinite impulse response, finite impulse response filters. From that FIR filter, digital filters, we will try to design the filter based on that LMSE, least mean square error. Okay, here, so the update tool for the SD is where using this all different mathematical analysis. So based on this all mathematical analysis, right, to decide the factors, or we can say that using this mathematical notation, so the SD is determined algorithm in the sense that where P, after that we can try to decide where R are assumed to be exactly known. But here all are involved with the mathematical notation. So thing is the practice, we can only estimate these functions. What type of functions here? The update rule for SD is where W of n plus 1 is equal to W of n minus of 1 by 2 mu g of n. Okay, from here it is using this all analysis, you can write it to decide the factor. The update rule for SD is, okay, with this, or we can consider where G is, but where the G is equal to where J of n. Okay, so we can consider this after G is ready to substitute here with this where W of n plus 1 is equal to W of n delta omega delta of W J of n is equal to minus what do you call like a 2p, okay, 2p plus or we can say that 2 into r W of n. Okay, so like this you can ready to use that update rule for SD. Okay, so what are the basic idea for defining this for analyzing this LMSE or least mean square error with the filter design? So the basic idea is the simplest estimate of the what you call expectation is major expectation is what do you call to remove the expectation term and replace them with what you call instantaneous values. That is nothing but we can consider that value. After that we can do that the gradient becomes will be varies or not. We can say that eventually the new update rule is satisfied or not, we right to decide. This is the way the estimate of the expectation is to remove the terms and replace them with the instantaneous values. So that is where R is equal to E of E of n into E of power h of n, where P is equal to E of n D of n with the, so where R cap of n is equal to E of n into E power h of n, where P cap of n is equal to E of n into D of n. Then the gradient becomes, by using this to remove the expectation terms, replace them with instantaneous values like R and P, R cap of n and P cap of n. Then the gradient becomes, okay, so like this mathematically it is analyzed. Del cap of W of cap J of n is equal to minus 2 U of n into D of n plus what do you call 2n of U E power h of what of n W of n. So like this eventually the new update rule is, okay, the rule where it is W of cap of n plus 1 is equal to W of W cap of n plus mu of un of D of n minus u of h of n W cap of n. So from this, the simple terms of the expectation will be appeared, and the gradient becomes, after that the new update rule is framed mathematically. This is the basic idea for implementing, for analyzing our least mean square error filter design. Okay, so with this, okay, so from this we can try to consider this like the gradient becomes, after that the new update rule is framed with reference to this no, there is no expectations. So one way are instantaneous, okay, samples ready to observe with the gradient becomes, and the new update rule is framed, is mathematically it is analyzed. So we try to expect these two, the gradient becomes and becomes like this value, and eventually the new update rule is, it is involved with there is no expectations and instantaneous samples, vertical samples. Okay, now try to use the basic idea. The filter weights are updated using instantaneous values. Where here that u of n, where v of n is given to that what a transversal filter w of cap n, and we will expect that our output is d cap of n. So meanwhile, it is where w of n is given to that what adaptive weight control mechanism. Okay, so once this mechanism is fed to this here, the transversal filter w of n. So now it is, after that that it is a factor, it is given to where v of n is observed, that d of n plus. Okay, so finally we are going to expect this mathematical analysis. W cap of n plus 1 is equal to W cap of n plus mu u of n e of n. Okay, with this it is identified that filter weights are updated using this instantaneous values using this particular block diagram. From that diagram 1, and compare these two, where it is click on this one, we have to verify that v of n is given to that z power minus 1. After that, we will write object u of n minus 1. Here it is given to that z power minus 1. So before that, here it is given to this one, and okay, and finally we have to observe this. Okay, according to this, okay, w cap of n, like this we are to design this all these two block diagrams. We'll expect this portion with this. Okay, so after that, what you call, so this is the outcome u of n minus capital M plus 1, and it is given that z power minus 1. So where u of n minus u plus m, it is given to here, where I to observe that w of n minus 1 here, m minus, where it is m minus 1, it is given to here. Okay, after that, before here, go on using this all way, it's already we have received from here, and so it is given to that. Finally, we are right to verify that d cap of n into like this. This is the design aspect, like filter weights are updating using this particular instantaneous values. This is the basic idea for analyzing this filter idea in the background. Where basic idea is where e of n, from that way, where e of n is equal to d of n minus y of n, where y of n is equal to, so it is what you call this value. Okay, and However, the term in the brackets is the error. Okay, so the error then is the here is you are ready to identify that SD value is involved here. Uh, W cap of n plus 1 is equal to W of n to mu u of n d power into n. So is the gradient. So the gradient before that, okay, with this gradient, okay, instead of this gradient, instead of this e of n square as a b, like this, we are right to assign where p is given to the mu is the summation here with minus mu, and it is minus w of n plus 1 given to here, and we have to verify that what we call w of n. Again here it is high and or raise like this, update the equation for least mean square. So with this update equation for using this blocks, okay, method of the steepest descent, uh, uh, we have the updated equation for the least mean square. So here it is where mu, where I and the previous diagram it is mentioned that I into z power minus 1 into I. So here we have to verify that cap of n. So by using the solved block diagrams with the mathematical analysis, updated the equations for method of the steepest vertical descent, or updated the equation for least mean square. Okay, so with this, the LMS algorithm will be analyzed. So least mean square algorithm. Yeah, you can try to verify that the biased or unbiased. Okay, so with this, if it is unbiased, what things are parameters are verified. Since the expectations are updated, the estimates will have the high variance. By using this all mathematical background and with reference to the block diagram of 1 and 2, so the expectations are updated, the estimates will have a high variance. Okay. Therefore, the recursive computations of each step weights in the LMS algorithm suffers from the gradient noise. Okay, so where it is coming from that LMS algorithm with based on these two ideas, with using this all mathematical analysis and block diagram oriented, the recursive computation of each step weight in the LMS algorithm, what we call, suffers from a gradient noise. Okay, so in contrast to SD, which is a deterministic algorithm, LMS is a member of the family of the what we call stochastic gradient what we call descent algorithms for analyzing this. So LMS has a higher MSE, like here J of infinity compared to the SD of J minimum, or if it is a Wiener solution as in n tends to infinity. Yeah, using this all higher MSE, that is where J of n to what you call J of infinity as n tends to what you call infinity. Okay, with this that difference is called excess mean square error. Here JE what do you call infinity. This is excess mean square error. Excess mean square error. Okay, the ratio JE of x of infinity by J minimum is called the misadjustment. Okay, misadjustment. Okay, hopefully, so J of infinity is a finite value, then LMS is said to be LMS least mean square algorithm is said to be what you call stable in the mean square sense. Yeah, if it is unbiased. If it is biased, so it is not satisfied with this all requirement here. So hopefully that J of infinity is a finite value and the LMS is said to be stable in the mean square error. Okay, so with this LMS will perform a random motion around the Wiener solution. Okay, so with this, so right to decide the factor with this initially that MSE, what do you call J omega, J infinity, okay, as a what do you call n tends to infinity, and we can say that it is J, that is E expected of what you call infinity, okay, okay, and ratio J infinity by what that ratio there should follow that J x of infinity by J minimum is called the misadjustment. So with this, hopeful that J infinity is finite, that J infinity should be finite, then LMS is said to be, if it is this value is finite, okay, so that LMS, our algorithm, that LMS is said to be what you call stable, stable in the mean square sense, stable in the mean square sense. So therefore, LMS will perform what do you call perform a random motion around the Wiener solution. So that's the measure in terms of the significance level. If it is the context based, which is deterministic algorithm, LMS is the member of the family of stochastic gradient descent algorithms. Okay, this is if we are initially that unbiased. Listen, the unbiased high variances of that gradient noise, it will be affected or suffer from that LMS algorithm, suffer from the gradient noise. Okay, it's which family it is, the contrast with this LMS deterministic algorithm, where LMS is the member of the family of stochastic gradient algorithm, whereas LMS has high MSE. Okay, so using this all algorithm based step by step mathematical involvement can decide that what you call that LMS is said to be stable in the mean square sense. Okay, where that LMS algorithm or LMS will perform the random motion around the Wiener solution. With this, where LMS algorithm, summary of the LMS algorithm, parameter, basically we're having that all parameter. One is what do you call that m value and mu value of that, we can decide the factor with m value, with the ms, with the s maximum, okay, and so on. If it is that using this mathematical notation where cap is equal to 0, or maybe sometimes if it is on using this all value with this typically from 0 to quarter, then that means we can vary that all variable used to select the appropriate value for this value. So the data is ready to analyze the LMS algorithm. The parameters m is equal to number of taps, that is the filter length, where m is equal to initially that what do you call 2 or 6 12 and so on. The filter length maybe increases that where mu step size is parameter, where 0 less than equal to mu less than equal to 2 by ms maximum, where S maximum is the maximum value of the power spectral density of the tap input E of n, and the finite length m is moderate to the large. So initialization, if a prior knowledge of the tap weight vector, okay, W of cap of n is available, use what do you call, use it, select an appropriate, okay, value for the W cap of 0, otherwise set the W cap of 0 equal to 0, where the data given U of n is equal to m by 1 minus 1 tap input vector time n, where U of n is equal to U of n comma U of n, okay, or you can consider that where v of n or u of n minus 1 or u of what do you call n minus m plus 1. Okay, like this, the given u of n is equal to m by minus 1 tap input vector at time n, and u of n or u of n minus 1 and so on, u of n minus 1 plus 1 power t, whole power capital T. So d of n is the desired response at the time n, okay, to be computed, where the w cap of n plus 1 is equals to what we call estimate of the tap weight vector at a time n plus 1. Okay, with this value you can decide the factor, the computation for n is equal to, for n value that small n or small n is equal to initially 0, what happens here 1 and 2 and so on. Compute this all value where n is equal to what we call 3, 4 and 5 and so on. So you like to compute this all where e of n is equal to d of n minus w cap of h of n and un. Okay, whatever your idea, based on that idea, the algorithm, the LMS algorithm, this is summarized the LMS algorithm. With this, w cap of n plus 1 is equal to w cap of n plus mu of u of n and e into of n. So this is the summary of the LMS algorithm. That means what type of parameter they are using. The parameters are based on m and mu. Okay, the number of taps are increasing or decreasing. How it has happened? Where what you call 0 less than equal to mu less than equal to 2 by m into s maximum, where s maximum is the maximum value of the power spectral density of the tap inputs u of n, and filter length m is moderate to the large. Like this, after we can use that initialization and what type of data is involved here, that where u of n minus 1, u of n minus m plus 1 and so on. Finally, we are to compute that for n is equal to 0, 1, 2, 3, 4 and so on. So e of n value, like this, we are to design the things implementing this LMS algorithm, least mean square filter algorithm. Okay, so where LMS algorithm involves the feedback connection. So once we have this all background, step by step procedure with m value and n value and SM maximum. Okay, how to involve in depth of this LMS algorithm involves the feedback connection. Okay, although LMS might seem very difficult to work due to randomness, so the feedback acts as the low pass filter or performs the averaging so that the randomness can be filtered out. Okay, the time constant of the averaging is inversely proportional to mu. Okay, so like this, actually if mu is chosen small enough, the adaptive process is made to progress slowly. This is one aspect, and the effects of the gradient noise on the tap weights are largely filtered out. This type of scenario is involved while we are implementing that LMS algorithm. There is involvement of the feedback connection, and the time constant of the averaging is inversely proportional to mu. If mu is chosen small enough, the adaptive process is made to progress slowly. And what are the effects using this condition? The effects of the gradient noise on the tap weights are large. Okay, based on that, the filter out will analyze in a graphically or maybe numerical value. If you try to design in real time, use the MATLAB or Python or whatever it is, the LMS algorithm is implemented in the real time or in maybe normal case or educational purpose. Okay, So here the computation's complexity of the LMS will be observed by using these constraints: involvement of the feedback connection and time constant of the averaging is inversely proportional to mu, where mu is the small, if the mu is large, and like this, the computational complexity of the LMS will be decided. Least mean square algorithm. So the LMS is very low, very attractive. Okay. So only 2m plus 1 is complex multiplication, and 2m complex additions are iteration. Like this, try to verify that our computational complexity, computational effects using this all involves of the feedback connection, or maybe constant way averaging, or maybe the mu values varies. The computational complexities of the LMS, okay, is very low, very attractive, only 2m plus 1 complex multiplication and 2m complex additions per iteration. Like what are the canonical model is involved? LMS algorithm for complex signal with complex coefficients as can be represented in terms of the 4 separate LMS algorithms for real signal with cross coupling between them. Okay, so write the input and or maybe desired signal or the tap gain or output error in the complex notation. Okay, so we can use this all mathematical notation. If you are writing this all in implementation canonical model, what are the effects of the LMS algorithm for either maybe using the complex signal or maybe using with the complex coefficients can be represented in terms of 4 separate LMS algorithms for real signal, real time signal. Okay, for this we have to use this mathematical notation. After that, we write implement in practically in real time. U of n is equal to u I of n plus j u q of n. Okay, with this, so the d of n is equal to di of n plus j dq of n. Okay, with this w cap of n is equal to like this. We have to analyze first way and second and third. Okay, using this all mathematical analysis notations. Okay, so our output response y of n is equal to y1 of n plus j yq of n. Okay, and finally that error e of n is equal to e1 of n plus j eq of n. This is the involvement of the canonical model with LMS algorithm for complex signal. Okay, where the input or desired signal or tap gains, output error in the complex notation. Okay, canonical model. So here y of n is equal to w cap of h of n u of n. So this then the relations between these expressions are okay. Y of n is equal to this value. Y1 of n is equal to like this, and yq of n is equal to like we can write this mathematical notation. That is that error will be displayed. E of n is equal to d of n minus y of n. Okay, with this scenario, so e I of n is equal to d I of n minus y of n. Okay, when you compare this y of n value with this that error with this y1 of n and yq of n and e1 of n and so on, usually can analyze that the relation between these expressions are evaluated mathematically, and manual operation and the practical operation is involved here. Okay, so with this wi of h n plus 1 and here these all values are analyzed in mathematical notation if you are using this particular model. So by using this all model, u of n is given to that these steps. Okay, and so it is fed to this one or the outcome of here. Finally, that y of n is received. This is one way. So next we can fed this, combine this one, W of W cap of Q1 is given to here with this what do you call this summer here. So now your Q of n is fed to this one, and here it's given to this. This outcome is connected to this one. This outcome is connected here. Finally, we have to verify that y1 of n and yq of n. Okay. Use this canonical model. How the complexity is involved or not. You can try to decide the factors. Okay. From these all values are involved here. Okay. Next, within the value, then the relations between these expressions. So canonical model is ready to implement in a practical way. The canonical model is U of n is we can use this way. Okay, it is fed. You can write observed here. Here that U of n is given to this one. Okay, so the outcome of this is fed to this one. Okay, after that we try to verify this mu value and the summation finally W cap of Q of n plus 1. Okay, so this is given to that. Okay, z power minus 1 I. Okay, after that we'll try to verify that this value which is given to this one, and finally try to verify this one and so on. This is one aspect. So where u of what do you call this n is given to this one, right to this here. Here right to verify that new value how it is varies. It is given to this one. Finally, right to verify that what do you call. So that if it is any complexity or maybe any error, okay, it's like this. You can give the feedback here. Z power minus 1 into I. It is given to that what you call W cap of I of n. After that, we have to decide that how it is. Where is that W cap of what you call n plus 1. Okay. Like this, right, to develop the canonical model. If you are having this all, so whether based on what do you call I of n, u I of n. So analysis of the LMS algorithm using this all block diagram and mathematical notation. Right, to analyze this analysis of the LMS. Okay, that LMS. What do you call? Analysis of the LMS. Although the filter is the linear combiner, the algorithm is highly non-linear and violates the superposition and homogeneity. This is the first analysis where you are using this one. Assume that the initial condition is so or analyze with this continuous using the weight error vector. Okay, so and its auto correlation effects how it is analyzed with this. F of ax plus by is equal to af, what do you call, f of what do you call, ax plus by is equal to what do you call, af of x, okay, x plus bf of y, then so right to where w cap of 0 equal to 0. Using this condition, analysis will continue using the weight error vector. Analysis will continue using the weight error vector. Okay. So after that, where the vector is, it is depending upon this mathematical notation. W cap of n is equal to what we call where n is equal to mu into what we call the summation, where the summation where I is equal to minus infinity to plus infinity. Okay, e of what we call I u of I. Okay, and that to write analyze the output response where y of n is equal to, okay, like this, where y of n is equal to mu into the summation I is equal to infinity to minus infinity to plus infinity e of I u of h of I u of n. So this analysis will continue using the weight vector, weight error vector. Okay. So with this, the output is this one. Where output is what you call here the output response of what you call here this output. Okay, and where this one is u of n is the input. So using you can go on using this input values where n is equal to 1, 0, 1, 2, 3, and so on, so on, how it is affect the output response. Analysis will continue using this weight vector, weight error vector, where that error vector here, here that error vector equal to w of n not equal to w of cap of n. Okay, with this, try to analyze. This all value will be analyzed within this. So what do you call this value is analyzed. K of n is equal to E of, so this is of h. Okay. So here we use the expectation. What type of expectation? However, actually it is what do you call the n symbol average. Okay. Next analysis of the elements, least mean square algorithm. We have so let this then the update equation. Wherever the mathematical notation for this can be written as, so like here we have w of w cap of n plus 1, or here it is what do you call that w of cap of n plus 1 is equal to w cap of n, okay, plus mu of u of n, okay, e of n. Let so e naught of n is equal to d of n minus w naught of h u of n. Then the update equation can be written as, so like the summation what you call, so sigma n plus 1 is equal to I minus u of mu into u of n, u power h of n. So like here mu of n into like this, that you can decide k of n plus 1 is equal to I of mu 1 and u of h of n, k of n with what do you call I minus u n mu n of n u h of n minus mu square into j minimum r. Okay, so that analyze convergence in the average sense. Okay, algorithm run many times study that how go on using this all values like equation, that update equation can be written as go on implement in real time, or maybe in normal cases analyze convergence in the average sense. Algorithm run many times study that in symbol here average behavior right to observe. Okay, so this is one way. Other way is using, by using it can be shown that where using this mathematical notation e of I minus mu into u of n, u h of n is equal to I minus mu hr. Okay, here this is nothing but here we use the expectation. However, actual it is the ensemble average. Okay, it can be shown that, so here it is n plus 1 is equal to I of mu or what do you call of n mu u of n to e naught of n. Okay, so like this, once on using this value k of n is equal to like this. It is, you can consider the small step size. Okay, the small step size assumption. Okay, next, a small step size analysis is based on, we have to use the different assumptions. First assumption is step size mu is small. How small? Because of we are going using this, all values are very small when compared to your assumption or your task for implementing our LMS filter acts like a low pass filter. Low pass filter, it allows only low frequency components opposes high frequency components. So LMS filter acts like a low pass filter with very low cutoff frequency. This is the first assumption. Yeah, second assumption is desired response is described by the linear multiple what you call regression model. Okay, that is matched exactly by the optimum Wiener filter. Because of this, using this normally the two-dimensional or three-dimensional or one-dimensional. In the signal processing or image processing, we have to use this second assumption. Okay, when where E naught of n so is the what you call irreducible estimate error, and with this third assumption, the input and input and the desired response are jointly Gaussian. Using the small step size analysis, with this we have to use the first assumption or second assumption or third assumption. Right, decide that our algorithm is suitable for your desirable way. Okay, so with this, where E naught of n is the irreducible estimate error, and we can consider that E naught of n, E naught of n minus 1, and so on. Finally, you can use the term where E naught of n value. Yeah, third assumption, the input and the desired response are jointly Gaussian. Okay, here small step size analysis we go for. Next, applying the similarity transformation resulting from the eigen eigen decomposition or on we will export. We do not have this term linear filtering. That is, then we have when this mathematically. Okay, E of n is equal to q power h of n, pi of n is equal to q h of naught of n, where v of n plus 1 is equal to I of minus mu a v of n plus pi of n. Okay, so v of pi of n is equal to 0, cap of n here. So we can prove that using in your home, use this all Bezier task, prove this all parameter with the small step size analysis, applying the similarity transformation, you resulting from the eigen decomposition. Okay, so this prove these relations. If it is possible, use this all notation, and that will try to analyze component of the v of n, how it is effects are correlated or maybe uncorrelated. We have to prove using this all small step size or algorithm assumption may be related to our assumption 1 and assumption 2 and assumption 3. Whichever you want suitable, your own interest, you can change that, you can prove that this particular relation. Okay. So using the same small step size analysis, component of V of n are uncorrelated. First order difference equation in notation, thermodynamics they are using. How they are using the solution? If it is, you can consider the stochastic force. If we are using this method, V of k of n, here it is V of k of n plus 1 is equal to 1 minus mu, what you call lambda mu, what we call mu lambda k. Okay, so with this, into vk of n plus pi k, where pi k of n, where go on using this all k value, where the k is equal to 1, 2, 3, 4 and so on up to m. Okay, the m, we know that all m value. Okay, so if it is first order difference equation, we will go for this, and the solution is involved here. Iteration from n equal to 0, vk of n is ready to, what is the natural component and forced component usually ready to observe. After that, we can decide the factor. So next, what are the learning curves? Two kinds of the learning curves: mean square error learning curve, that is mean square deviation MSD learning curve. So ensemble the average result of the many infinity realization or average. Okay, what is the relation between MSC and MSD? Try to analyze. So with this, analyzing mathematically, mean square deviation MSD learn curve, it is based on the mathematical formula d of n is equal to e of that sum of vertical and d of n is equal like this. Assembled results of many realized or averaged. So if it is for mu equal to small, it is mu equal to large, and medium of that. So d of n is approximately equal to like this way, and where is equal to d of n is this one, and d is equal summation the k equal to 1 to m. Okay, e of vk of n square. Okay, if for mu equal to small, if you go on using this all mu value equal, mu is equal to large, what happens when mu equal to small? Okay, like this learning curves will be reflected. Two kinds of the learning curves: mean square error learning curve, or maybe mean square deviation MSD learning curve. Like this, it is affected. After you try to decide that MSC versus MSD. Okay, so learning curves are based on this all analysis. E of n value under this assumption of the previous one, directly you can write it to decide the factor. Okay, like this, the mean square deviation d is lower upper bounded by the excess MSC. Okay, they have similar response, so decaying as the n grows. This is the learning curves are reflected. That is mathematical analysis where lambda minimum less than or equal to lambda k less than or equal to lambda maximum. With this, you can ready to analyze. One is this one, and d of n, and this value, or initially we are ready to receive this one, or finally this one. Of that, you can decide this mean square deviation d is low upper boundary by the excess MSC. They have similar response, decaying as a n grows. Okay, with this, okay, convergence for mu equal to small, and the, okay, so right to analyze this particular value. Okay, you will try to implement using MATLAB or Python. We will continue next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.